Okay, so hello everyone and welcome to one of our last editions of extremal and probabilistic combinatorics webinar. This is because we will be taking summer break in July and August. As usual, we will have our speaker speaking for around 60 minutes. Please don't hesitate to ask questions during the talk if you have any. If you don't want to be recorded, then you can type them in the chat. I can read them out to our speaker. And so now it's my pleasure to introduce Xizhi Liu from University of Illinois at Chicago, and he will be talking about hypergraph Turan problem and stability. So please.
Thank you. Thank you for the invitation. Okay, so hypergraph stability, yeah. So before I started, so this is the work done with Dhruv and Xizhi. And the outer line, you can see there are going to be infinitely many definitions in this talk. Yeah, okay. Okay, let's start with the Turan problem. The Turan problem is you take it's basically counting the number of edges in a graph or hypergraph, but you have to put some constraints on your hypergraph. Let's say you do not want to have some subgraph. Say you do not want your graph to have a triangle. Then you want to know how many edges can you have in such graphs. And so this is a typical Turan problem. Some definitions, you can define the Turan number, which is the maximum number of edges in your graph. F-free graph means you forbid every member in F. And sometimes we only care about the edge density. So when the number of vertices is going to infinity, what's the value of the edge density in your extremal configurations? So we define pi of F is the limit of the edge density. And in this talk, we only care about families whose Turan density is not 0. And for this kind of family, we call it non-degenerate. So if the Turan density is 0, then it's degenerate with another big topic in extremal combinatorics. Okay. So for Turan problem, you have a forbidden family F, and you have some graphs which does not contain F with the maximum number of edges. So this kind of a graph, a hypergraph, we call it extremal graph, extremal configurations. And so it turns out most extremal configurations usually have very simple structure. So how do you define the structure? We say a hypergraph is G colorable. Yeah, so G is another hypergraph, a graph. For example, it's G colorable if you can find an edge in some blow-ups of G. For example, if your G is K2, 2 vertices, 1 edge, so it's a K2. So what is a K2 colorable graph? It's very simple. It's just a bipartite graph. Because if you blow up K2, blow up means you replace every vertex by a vertex set, and the edges becomes a complete bipartite graph. So K2 colorable means it's a subgraph of a complete bipartite graph. In other words, it's just a bipartite graph. And for hypergraph, let's say you have 3 vertices, 1 edge, so K3, a complete 3 graph on 3 vertices. And if you blow this hypergraph up, you will get a complete 3-partite 3 graph. Replace every vertex by a vertex set and replace this edge by all possible crossing edges. And the subgraph of this blow up is just a 3-partite 3 graph. So this is the meaning of G colorable. And so the structure is basically the same as K2 or K33. The structure is basically the same as G. A simple observation is if your graph is key L colorable, so key L is an L vertices complete graph. So for example, if L equals 3, if it's a K3 colorable means it's a 3-partite graph. The 3-partite graph. Not necessarily complete. 3-partite graph. So if a KL colorable, then it's L partite. They are equivalent. So let's go to some theorems in graphs. So yeah, so the most famous result in Trend problems is the Trend Theorem. So Trend determined the Trend number of all complete graphs. So it's basically this number. So if you forbid L plus 1 vertices complete graph in your big graph, then the number of edges you can have is bounded by this number. In other words, the Trend density of the complete graph is this one. Is 1 minus 1 over L. And the extremal graph also determine the extremal graph is just the key L colorable. In other words, L partite graph with the maximum number of edges. In other words, it's a balanced complete L partite graph. This is also called the Trend graph. So for example, if you forbid a complete 4 vertex graph, so this is your forbidden graph. Then the extremal graph is a balanced blow up of a triangle. Before. So this is the extremal graph. You just need to remember the extremal graph for KL plus 1 is the KL colorable. Then with some trivial calculations, you know everything about the Trend number, Trend density. So then Erdős and Stone generalized Trend theorem to every family of graphs. So F is now the family of a graph. It turns out the Trend density of F is basically determined by its chromatic number, chi of F. So what's the chromatic number of a family? It's just the minimum chromatic number of its member. Say your F is So you have a triangle, you forbid a triangle, you forbid a K4, anything. The chromatic number of a triangle is 3, the chromatic number of a K4 is 4. And you just need to look at the minimum chromatic number of its member. That is the chromatic number of the family itself. For example, if your F is K3 and K4, then Erdős-Sós theorem tells you the true density of F is 1 minus 1/3 minus 1, which is a half. Okay, so this theorem basically tells you everything about the Trend problem in graphs. And for any family, you can determine its Trend density using this theorem. And then people are not happy with the Trend density itself. They want to know the Trend number. So how do you go from the density, the asymptotic value, to an exact value? So there is a method invented by Erdős and Simonovich called a stability method. So I'm not going to say how to use the stability, but I'm going to say the stability itself. Now it's becoming an interesting topic itself. So, so what is a stability? The stability is firstly you forbid a family, then you forbid a triangle, and then you know you take any triangle-free graph and say you know the number of edges in your graph G is very close to the extremal value. For triangle, it is the same as the number of edges is very close to the density, the edge density is very close to a half. Epsilon is a small constant. Then the stability theorem tells you the structure of G. The structure of G can only look like this graph. Means it's essentially a complete bipartite graph. But you will, since the number of edges is only close to the extreme value, there will be some missing edges. So the blue edges are not in your graph, and the red edges are in G. That's the red edges is the reason that G is not a bipartite. But G is very close to a bipartite graph. So the red edges, the number of red edges is very small. The number of blue edges is small. So most edges are between these two parts. So stability is from the number of edges to the structure of G. So this is one kind of stability result. But actually there is another kind of stability result. I'm going to call this Aes Theorem. Another type of result is first, you know, it does not contain some family, say a complete graph. And then instead of the number of edges, you know the minimum degree is big. For L equals 2, the minimum degree, for L equals 2, this is n over 2. So you know the num is say G is a triangle free, and the minimum degree is close to n over 2. Then this theorem tells you it's not just close to a bipartite graph, it's actually a bipartite graph. There is no bad edges anymore, no such edges. It's a pure bipartite graph. So here you why this one is a stability theorem, I will explain this later. So now you have two stability theorems. In fact, one implies the other. You can guess which one is stronger. I'm going to explain this later. So for this page, you have a stability result in terms of the number of edges, and a stability result in terms of the minimum degree. So two kind of stability. So now I'm going to define more stability. So as usual, you have a forbidden family F. You have your favorite F-free hypergraph H. And in addition, you have a summer family G. For example, you can think of F as a triangle, K3. And G is the collection of all bipartite graphs. In other words, K2 colorable graph. So G is kind of the collection of all extremal-like graphs in terms of F. Okay, so what is the edge stable? So F is edge stable if whenever you have this conclusion. So if the number of edges in H is close to the extremal value, then you can remove some very few number of edges to make it, say, bipartite. So you remove some bad edges, then you get a bipartite graph. And vertex stable is instead of removing edges, you can remove a very few number of vertices to make it a bipartite. Then the structure of H is basically look like this. You can remove some vertices to make it a bipartite. And the degree stable means if the minimum degree of H is big. This is the average degree in the extremal graph. If the minimum degree is close to the extremal average degree, then H itself is bipartite. So this is three kinds of stability. In fact, you can this property is getting stronger and stronger. So if you know the degree stability of F, then it implies vertex stability of F. Then it implies edge stability. Let me explain this one. The vertex stability implies edge stability. Take the triangle as an example. So this is the set of vertices you removed. You remove the delta n many vertices. Then instead of removing vertices, you can remove edges. So which kind of edges should you remove? You can remove edges that have one vertex inside this bad vertex set. So you remove all edges, look like this. After you removing these edges, you get a bipartite graph. But how many edges you removed? It's only delta n times n, delta n squared, many edges. So vertex stability implies edge stability. And the degree stability implies vertex stability. Why this is true? So I give you a graph H with many number of edges. With many number of edges. Then you need to tell me, let's say F is a degree stable, and I give you a hypergraph H with a with many number of edges. Then you need to tell me how many what's the vertex set you are going to remove. And here is a choice. You can remove this vertex set, this vertices with a small degree. How small is 1 minus epsilon to the one third. So you just need to remove the vertices with a small degree, then you will get a bipartite graph. And in order to show it has vertex stability, you just need to argue this ZH is small. Why ZH is small? Because you have too many number of edges. You cannot have too many vertices with a small degree. Yeah. Okay. So this is the relations between this kind of stabilities. So what you need to remember is just degree stability is the strongest stability. Yeah. And now go back to graphs. For graph, what can we say about this three kind of stability? Can you characterize the families with this kind of stability? The answer is yes, and it's already yeah, we think it's already well known. Yeah. So let's define a graph F is edge critical. If you can reduce the chromatic number by removing one edge, say C5, this 5 cycle is edge critical, because if you remove this red edge, you get a bipartite graph. The chromatic number goes from 3 to 1, 3 to 2 after you remove this red edge. And you can also define matching critical. Matching critical is if you can reduce the number of chromatic number by removing a matching. So what is a matching critical graph? Here is one example. Your graph is the disjoint union of 2 5 cycles. After you remove this red edges, so it's a matching of size 2. After you removing this matching, the chromatic number goes down. So this graph is matching critical. Similarly, you can define edge critical and matching critical for a family. Is determined by the member in F with the minimum chromatic number. So you look at the member F with the minimum chromatic number. If F is edge critical, then the family F is edge critical. If F is matching critical, then the family F is matching critical. And one theorem is for a family of graphs, the degree stable is equivalent to edge critical. So C5 is degree stable. And vertex stable is equivalent to matching critical. And so this 2C5 is vertex stable. So this is a theorem about the graphs. So for graph, you basically know which kind of family is degree stable, which kind of family is vertex stable. So this is graphs. And now we go to hypergraph. So it's so hypergraph terrain problem is a bit harder than the graph terrain problem. So it's impossible to kind of to have a theorem look like this. It's impossible to characterize which kind of family is a degree stable, which kind of family is a vertex stable. But there do have some kind of general method you can use to prove stability. And for the edge stability there, the theorem of Noreen and Liana is So it's a general method you can use to prove the edge stability of some family. So edge stability means remove some edges. And for vertex stability, Pioco have a method. It's a general method you can use to prove the vertex stability. And his argument uses the Zikov symmetricalization. And what we have is a method for degree stability. Our proof uses what we call the percentric. I'm not going to say the proof itself. I'm going to say how to use our result. So remark is in fact, our result is contains Pioco's method. No, contains the Pioco's result. So everything can be proved using his result. His method can also be proved using our method. But we cannot handle number one, edge stability. There do have one exception. The generalized triangles in hypergraphs. This family have edge stability, but do not have degree stability. So our method cannot handle this this family. But there do have many applications of our result. Here is a list. You can apply our method to this result to improve their stability result. So there are going to be more definitions. So I'm going to say the result first. Then I will explain what this definition. So you take your forbidden family F. It's non-degenerate. The trend density is greater than 0. And you have another family G, which is the set of hypergraphs which contains the candidates for the extremal configuration. So you take F is a triangle, K3, and G to be all bipartite graphs. Why we take a bipartite graphs? Because we know the extremal graph is a bipartite. So you take F to be triangle, G to be bipartite graphs, all bipartite graphs. So if you check the here you have 3 conditions. After you check these 3 conditions, then you will know some stability about F. So what are these conditions you need to check? First, you need to check F. So F must be blow-up invariant. So what is a blow-up invariant? Means if you take say if you take a triangle free graph, let's say you take C5. C5 is the triangle free. After you blow this up, it's still triangle free. So blow up will keep the F freeness for some F, not for every family F. So you need to restrict your family to this class. F the blow up must keep the F freeness of F. F freeness of your graph. If your family have this property, then we say it's a blow-up invariant. Then there are 2 conditions about the G. First, the G cannot be too small. So you cannot take G to be empty set. So G should contain some special kind of F-free graphs. So and the the property of members in G is defined using the symmetricalized stable. I will explain this later. And the third condition is F is a vertex-extendable. So there's just some fancy names. I will explain them. So after you check these three conditions, then you can say, okay, your F is degree stable. In other words, every F-free graph with a large minimum degree is contained in G. So for triangle, what does this mean? Every graph with a large minimum degree is bipartite. It's exactly the Aes theorem. Yeah. So if you take F to be the complete graph KL plus 1, the G to be the L-partite graphs, and you apply this theorem, you will get the Aes theorem. Okay, this is just some some weird definitions. I will explain this in the next slide. Okay, blow-up invariant we already defined. The blow-up keeps the F-freeness of your graph. So what is a symmetricalized stable? Okay, some definitions about a hypergraph. So first we are going to define what is a symmetricalized hypergraph. So what is a symmetricalized hypergraph? Yeah, first we need to define the shadow. So think about your hypergraph is actually a 3 graph. Every edge has 3 vertices. Then the shadow of edge now is a 2 graph. What is a shadow? Let's look at this example. Shadow means you look at the pair of vertices that is contained in some edge. So for example, if your 3 graph look like this, and you take the shadow, and you look at the pairs that is contained in one edge, you will get this graph. Yeah. So the edges in the shadow is the pairs that are covered by some 3 set. And if you look at this hypergraph and take the shadow, you will see every pair of vertices is contained in some 3 set. So the shadow is now a complete graph. So if the shadow is a complete graph, then we say the hypergraph itself, the 3 graph is 2 covered, because every pair is covered by one edge. So this is a 2 covered hypergraph. Yeah, instead of define link, I can tell you what is a symmetricalized hypergraph. So what is a symmetricalized hypergraph? So actually the symmetricalized if it's a blow up of a 2 covered hypergraph. Yeah. For example, if your hypergraph will so this is your hypergraph. It's 2 covered, and the blow up of it is symmetricalized. So symmetricalized hypergraph is the equivalent to say it's a blow up of a 2 covered hypergraph. Yeah, but if you restrict the definition to graphs, it's very simple. Symmetricalized graph is equivalent to complete multipartite graph. So it's a general extension of complete multipartite graph to hypergraphs. say complete four-parted graph. Any complete multi-parted graph is a symmetricalized graph. So this is a symmetricalized hypergraph. So what does this mean to say a family is a symmetricalized stable? Yeah, let's take an example. Let's say you look at the triangle, and you take your G to be the collection of all bipartite graphs. Then we can say triangle is a symmetricalized stable with respect to G. Why? Because every triangle-free graph, every symmetricalized triangle-free graph is a complete bipartite graph. Let's think about this. So every complete multi-parted graph that does not contain a triangle must be a bipartite graph. Why this is true? Suppose your H is say a four-parted graph. Then it must contain a triangle because you can take a vertex from each part. Then you will find a triangle. So the number of parts in H must be smaller than 3, means it has only 2 parts. So H must be bipartite graph. So yeah, so every so that's an example for symmetrically stable. Means yeah, actually it tells you something about G. As we said before, G should not be too small. So G should contain all symmetricalized F-free hypergraph. So for the triangle case, G should contain all complete bipartite graph. But here G is a bit larger because it contains all bipartite graph, not necessarily complete. Okay, so this is a symmetrically stable. Yeah, then the third definition, the vertex-extendable of F. So what is a vertex-extendable? Yeah, let's look at one example. Suppose I give you a graph H. I tell you 3 conditions. First is the triangle free. Second, it has a larger minimum degree. And the third condition is you know almost the structure of H, except one vertex. So what does this mean? After you remove a vertex V from your H, you will get a bipartite graph. So H minus V is a bipartite graph. So you know 3 conditions. H is a triangle free. H has a bigger minimum degree. And H minus V is a bipartite. So you know the structure of H remove one vertex. What can you say about the structure of H itself? Can you say H is a bipartite? Yeah. So here is a question. Is H bipartite? So can you say H is a bipartite from these 3 conditions? The answer is yes. So let's look at this claim. So suppose you want to say H is a bipartite. What does this mean? It means V cannot have neighbors in both parts. I claim this is a wrong picture because in this picture, we have neighbors in both parts. So why this is a wrong picture? Let's prove it. So first from the minimum degree condition, you know, we have many numbers, many neighbors in these two parts. And by pigeonhole, you know, at least half of it is contained in some part. Let's say you have many neighbors in this part. Let's say you have at least n over 6 neighbors of V in the left part. Then can you have at least one neighbor inside the V2, inside the right part? The claim is no, you do not have a neighbor inside the V2. Why? Say you have a neighbor U2 in V2. Then what is the contradiction? The contradiction is you will find a triangle. So where is the triangle? I claim this is a triangle. There exists a vertex in this in the neighbors of V in V1, such that U1 is connected to U2. Why this is true? Again, by the minimum degree condition. U2 have about n over 2 neighbors. But where is the neighbors of U2? It cannot be here because this part is bipartite. So the neighbors of U2 can only be in V1. So U2 have at least about n over 2 neighbors in V1. And this the neighbors of V in V1 is big, is at least n over 6. So you will see there will be some overlap of the neighbors of U2 and the neighbors of V1. So means U2 will have a neighbor inside this part. Then this is a triangle. But actually it's a triangle free, so this cannot be possible. It means V cannot have neighbors inside V2. So this neighbor does not exist. Okay, now we know V can have neighbors only in one part. This means H itself is bipartite. So the answer is yes, H is bipartite. So what does this mean? So the whole proof shows if you have these three conditions, then you know the structure of H. Triangle free, large minimum degree, and the structure of almost all of H implies the global structure of H. Okay, now let's go back to the definition. So we say F is the vertex extendable with respect to G. So think of F is a triangle, G is a bipartite graph, G is a collection of all bipartite graphs. If you know, if every F-free hypergraph with large minimum degree satisfy this property, the structure of after removing one vertex tells you the structure of H itself. Yeah. Okay. Yeah. Now let's go back to the theorem itself. So take a forbidden family and check three conditions. Yeah, let's do one exercise. Let's take F is the L plus one vertex complete graph. The G to be all L-partial graph. And let's check these three conditions. First, the blow up keeps the KL plus 1 freeness of your graph. That means the blow up will not create a bigger click. So this first one is a trivial. Complete graph is the blow up invariant. And now second condition means you should check if G contains all symmetricalized KL plus 1 free graph. So what is a symmetricalized KL plus 1 free graph? So symmetricalized graph means a complete multi-part graph. So you need to figure out how many parts can you have in a KL plus 1 free complete graph. Apparently, you cannot have more than L parts. So you have at most L parts. Otherwise, you will have a KL plus 1, a copy of the KL plus 1. So the second one is also true. G contains all symmetricalized KL plus 1 graph. And the third one is you need to check if F is a vertex-extendable with respect to G. So what does this mean? Similar to the triangle case, you need to check this property. So first, you take any graph, H. KL plus 1 free with a larger minimum degree. And you know the structure of H after removing one vertex. H remove V is L-partite. Let's call this EPC. So you need to check, can you determine the structure of H from these three conditions? KL plus 1 free, larger minimum degree, and the structure after removing one vertex. Let's say. In other words, can you find one part where you can put a V inside? In other words, can V have all neighbors in all these L parts? Can V have neighbors in L parts? Similar to the triangle case, it's easy to argue it can have neighbors in at most L plus L minus 1 part. Let's look at the triangle case. So this V can have neighbors in at most 1 part. It cannot have neighbors in both parts. Otherwise, you will have a triangle. Yeah. So this is the three conditions. After you check these three conditions, then you can say, okay, F and now KL plus 1 have the degree stability. Means every KL plus 1 free graph with a large minimum degree is contained in G, contained in the family G. In other words, H is the L-partite graph. So this theorem will imply the Aes theorem. Okay, this is not the most general form of the theorem. So this method was designed to handle the family with more than one extremal graph. In graph case, there is only one extremal graph, which is the trend graph. Every family has a unique extremal graph. But for hypergraph, they do have some families with more than one extremal graph. It has two different extremal configurations, two different hypergraphs with the maximum number of edges. So how do you prove stability for this kind of family? It's very simple. You just need to expand the family G. Here is your family G. Let's take this as an example. So for this family, for this F, for complete graph, we just take G to be our key L colorable graph. Because you know the extremal graph is the key L colorable. Now for multi-extremal configuration families, you can take G to be the union of G1, G2, G3 to G, let's say M. So you have M extremal hypergraphs. You can take G1 to be the collection of all, let's say, so what's the notation? Let's say H1 colorable hypergraphs. And G2 to be H2 colorable hypergraph. And GM is a HM colorable hypergraph. For example, just for example, you can take G1 to be triangle, to be 3-parted graphs, G2 to be 4-parted graphs. It's determined by your extremal graph. Then you just need to check this 3 conditions for each of them, for each G1, for G1, G2, G3 to GM. So check these 3 conditions for G1 for each of them. Then you can say something about the stability of F. Then you know if you take a F-free hypergraph with a larger minimum degree, then your H must be contained in some of these GIs. You know the structure of H. Yeah. But in fact, you can also handle families with infinitely many extremal configurations. Here, the M, even though I wrote M, but actually you can take an index set, which is infinite. So we do not require the number of extremal graphs to be finite. Yeah, but we only know the applications in finite case. Let's skip the hypergraph example and go back and go to the remark. So I said before there are many applications of the stability result, the method, but there do have some exceptions. Some families we know it has a degree stability, but we cannot use our method to prove it. A famous example is the funnel plan. So it's a 3 graph with 7 vertices and 7 edges. So if you forbid this 3 graph in your hypergraph, then the maximum number of edges you can have is bounded by this extremal graph. The extremal graph is a complete bipartite 3 graph. You can have only this type of edges. So the final plan has the degree stability but we cannot no, we cannot prove it using our method. Actually, the stability is proved by two groups of authors. Another one is the so-called F32 is this third graph. It has 5 vertices, 4 edges. It's 4 edges. And the extremal graph is a semi-bipartite third graph. So that you have only this type of edges in your extremal graph. So it also has the degree stability, but we cannot prove it. Yeah, so it would be interesting to handle these two families using our method. Then everything has a degree stability can be handled using our method. Other applications of the method instead of the result, I mean the method that we prove our result. It would be interesting to see if you can prove a similar stability result for other problems, the inducibility. Can inducibility have some kind of strong stability using our method, or digraph? Can you prove this kind of a theorem in digraphs? Okay, that would be all for today. Any questions?
Thank you very much for a very nice talk. Could I ask the audience to unmute themselves and give Xizhi a round of applause?
Let's go to the
Are there any questions? So I have a question regarding your last slide.
Yeah.
So in undirected graphs, you don't need any of your machinery because things are so simple. But
Yeah.
digraphs are quite easy as well, aren't they? I'm not sure. So this is more of a question. So
digraph, I do not know. Yeah, actually, I do not know very much about the digraphs, but for inducible, yeah. So the intuition is that if you can do some kind of Zykov symmetricalization, then there have a chance that you can prove some similar result. So our method is built on the Zykov symmetricalization, but yeah.
okay. Thanks. And maybe you said it, but I just didn't notice. Were you able to get any new family with this method?
No, the answer is no, because yeah, the method is for stability, so not for the Turan number. So in fact, if you know your family, if you know your family have these 3 properties, for say using some magic method, you know, F satisfy these 3 properties, then it's a kind of a trivial to determine the Turan number. So in some sense, our method is for the kind of some trivial families, like some extension of cliques into hypergraphs. Yeah.
Okay.
Yeah. So it's only a method for strong stability. Yeah.
Thanks.